Okay, everyone. So we're going to talk about 7.1 in the text, which is using U substitutions, which is really just undoing the chain rule. But okay, let's get into it. So as a quick refresher, antiderivatives we should know. There's stuff involving the power rule. So inside the integrand, we have x to the 1/4. So if I add 1, it'll be x to the 5/4. And then dividing by 5/4 is the same as multiplying by 4/5. And I have a plus c. And then there's trig functions, which you need to be very comfortable with. So because the derivative of sine is cosine, that means the antiderivative of cosine is sine, which is a bit of a mouthful. There's exponentials, which, okay, we often use e. You'll see e 99% of the time. But just to remind you, if you have a different number as the base, such as 3, then you have to do, it's still 3 to the y, but you have to divide by the natural log of the base. So natural log 3, and then plus c. Okay, and the last main type that we see is natural log. So this is natural log of v. Plus c. And there are others that I could have included on this list, but eventually you just have to chop it somewhere. Another pretty common one is, let's see, maybe it's something like this. And it's an inverse sine function or an arc sine. Okay. But these are the integrals that up until now we know how to do, and they're really not that complicated. But we want to be able to do nastier things or messier integrals, right? So, let me see if I can move my video a little bit. There we go. All right, so what all three of these integrals have in common? Somewhere within them, there is a function whose derivative also appears. And that is a sign that a chain rule is happening. So similarly here, if I were to take the derivative of 6, so ddt of 6t cubed plus 5, that light is reflecting right in my eyes, just so you know, thanks. If I were to take that derivative, I get 18t squared, and that's exactly what's here. Right? Now, in red, okay, if I were to take the derivative of x squared, I don't get exactly x, I get 2x. But it turns out if you just have to rescale by a constant, that's good enough to signal that a chain rule happened. Okay, and let's just look at one more where this is going on. So if I were to take the derivative ddw of w minus the natural log of w, I would get that 1 minus 1 over w that we're seeing. And so the fact that we see in all these examples a function and it's, okay, sorry, we're taking an integral. Within this integral, somewhere in here, there's a function and its derivative appearing. That's a sign you have to use U substitution. In other words, it's a sign that a chain rule occurred and we have to undo it. Okay, so, right, as a reminder, chain rule, if we begin with a composition, f of g of x, and we take a derivative, we're going to get f prime of g of x times g prime of x. Right? Okay, if you take an antiderivative, if you start here, if you have a function, maybe that function is cosine. And inside of that cosine, you see some kind of function. Oops. So w minus natural log w. And outside of that, you see the derivative of that function. Then that tells us how to go back. That tells us how to compute the antiderivative. I need to move my, there we go. Right, I can see that in here, this is what I want to be my g. This is my g prime. So this, the cosine, must be my f prime. It must, in order to fit the way everything looks. So it must be the case that f, the antiderivative of this, is sine. Right? I'm just going back and using this relationship from before. So if I put it all together, I now have an antiderivative for my f part, and I know what's playing the role of g and what's playing the role of g prime. So if I were to compile f of g of x, well, that's sine of, and here's g, it's w minus the natural log of w, and I could say plus c, but you can check, take the derivative of this, see if you get what's inside of this integral. Okay? It should all work out. But let's make this a little bit more algorithmic with what's called U substitutions. And let's just do, literally all the rest of the class is going to be examples. And if you look at this section in the textbook, that's basically the way it works too. It's just a slew of examples and then a slew of problems. You just need to get used to this technique. All right, so here we go. I have quite a few examples to run through. So once you feel like you get the hang of it, just stop the video and go try on your own. But okay, really popular one, tangent of x. So first we need to rewrite tangent as sine over cosine. Okay. And the derivative of sine is cosine. The derivative of cosine is negative sine. And that sort of makes it a little unclear, like which function do I want to use as the original versus as the derivative? Like which do I want to use as g versus g prime? And I already know the answer. So let me just demonstrate the U sub technique. So I choose one, all right? And I might get it wrong. And we'll address that maybe some other time or maybe in one-on-one. But I pick a function that I want to be playing the role of my g, okay? And it's a little irritating that when we introduce the chain rule, we use f and g, but when we introduce U subs, we use u. So really what's going to happen is we're going to have something that looks like f prime u du instead of f of g of x, g prime of x. But okay, so you pick a function that's going to be that g or that u, it's cosine of x. Then you take the derivative. So the derivative of u, I could say with respect to x, is sine of x. Okay, this is where things get a little bit hand-wavy for your first time in calculus. And what we can often say is just multiply the dx over, or sometimes people just jump straight from the first line to where I'm going, but they'll write du is equal to sine of x dx. Okay. And okay, notice I have a sine of x times a dx occurring. I have exactly this. So now I do substitutions. And so where I see a cosine appear, I swap it out with u. So I have 1 over u. And where I see sine x times dx, I swap it out with a du. Okay. Now this is a function, 1 over u, that we know how to take the antiderivative of. It's natural log of the absolute value of u plus c. But now I have to back substitute and put back in what u is. So this is natural log of the absolute value of cosine of x plus c. Here's my final answer. Okay. All right, let's do a few more. All right, this time it's a little bit clearer. I have a function, x squared, and some version of its derivative, a scaled version, appears right here. So this tells me I want my u to be x squared. Okay, now I take a derivative. Du is equal to 2x dx. All right, and, oh, I should have written a dx here, sorry. So in this integral, I have an x with a dx. Here's an x with a dx. I don't have that too, but that's okay, just divide it over. So 1/2 du is equal to x dx. And now I can make my substitutions. So instead of e to the x squared, I have e to the u. And instead of x with a dx, I have 1/2 du. So now I pull the 1/2 out. And I have antiderivative e to the u du, which is just 1/2 e to the u plus a constant. And that's 1/2 e to the, and then I plug back in what u is, which is x squared. Okay. And just to make this one a little bit different, let's go ahead and, let's see, so limits on this, x can't be too big. Like we could do, oh, let's just make this a plus. That makes our life a lot easier. Okay, let's go from 0 to 1 here. Let me show you a full U substitution. So, okay, again, I have a function right here, and its derivative appears. So that original thing is what I want as my u. So I have u is equal to 1 plus 4x squared. Now du is equal to 8x dx. And just like in the last problem, really all that I have up top is my x dx. So I need to get that by itself. So I have 1/8 du is equal to x dx. And so now we can begin the substitution. And let's see, so on bottom, I have square root of u. And instead of x dx, I now just have a du, but there's also this 1/8 here, and I'm just going to put that out front. Okay, and I can put a 1 on top. Okay, now, words of caution. Right? These limits that we started with, those are x limits. This is saying x is equal to 1. This is saying x is equal to 0. But now, since everything is in terms of a new variable u, we need to figure out what u is equal to. These are u limits. But u is a function of x. And so all we really need to do is plug x equals 0 and x equals 1 into this function, and that'll give us our new limits. So when x is 0, we have 1 plus 0, so we get 0. Right? Sorry, we get 1. And where this came from, this was 1 plus 4 times 0 squared. I used my old x limit. When we play the same game, I plug in 1, I'll get 5. This is 1 plus 4 times 1 squared. Okay, so now we have an integral that we can solve. And let's see, so this is a u to the negative 1/2 power. So if I add 1, I'll get u to the positive 1/2 power. And I have to divide by that 1/2, which is the same as multiplying by 2. But then I have this 1/8 out front, so I have 2/8. Okay, but there it is. There's my antiderivative. And now I have to evaluate between 5 and 1. And so let's see, that's my 1/4, just canceling the 2 and the 8. And then I have square root of 5 minus square root of 1. So here we go. There's my answer right there. Okay. There is another way to do this. So let's go back up here for a second. And if there were limits on this integral, so let's just say we go from 0 to 1 of x e to the x squared dx. So another way to solve this, if you don't want to have to swap out your limits of integration, if you don't want to have to change these guys, then what you can do is you first, step 1, figure out the antiderivative for the function of interest. Okay. All right, here it is. Once you have that antiderivative, then you come back and you use your old x limits. And so I have 1/2 e minus 1/2. And then would be e to the 0, this is e to the 1, but e to the 0 is 1, so whatever. Right, so in other words, right, what's the point of me saying this? If you're given limits and there's some kind of integrand where you have to use a u sub, you have two choices. You can figure out an antiderivative by ignoring limits and just doing your u substitution, and then plug in limits at the end, or you can change your limits and just keep on going. Okay? All right. So both of these problems have very similar flavor. What's very nice, let me look at this one first. You can simplify, actually, you know what? Let's ignore this one. That'll be handled at this very last example that I have. So let's just do this last example first. So let's pretend we have a function who we know the antiderivative of. So like I know the antiderivative of little f is big F. And then we're interested in the antiderivative, and now it's not just f, but we have f of some kind of linear combination, ax plus b. All right, well, I would let u equal ax plus b, and right, a and b are constants. So now du is equal to a dx, and again, that's just a constant, like 2 or 3, right? So what I get, right, what can I do? What can I do? here's a dx, here's a dx. So let's solve for that dx by dividing the a over. I have 1 over a du is equal to dx. Okay, now let's do the substitutions. I have f of u, and this dx is gone. It's now replaced with 1 over a, which I'll put out front, times du. There we go. Now that 1 over a comes along for the ride, and the antiderivative of little f is big F, so I have big F of u. But now if I plug back in what u is, it's 1 over a big F of ax plus b. Okay, so notice the plus b doesn't appear to change anything, but the multiplication by a ends up making us have to divide by a in the end. And what I mean by all this is, right, when I write this statement that I have circled, what it really says is that the antiderivative of f of x dx is big F of x plus c. I should have plus c all along. Right? Knowing this, if we change that integral by changing that the argument, the x thing, a little bit, we know how the antiderivative changes. So, okay. An example of that is what I have crossed out up here, but let's just do it really quick. If u is x plus 7, then du is the same thing as dx. And this integral becomes the integral of u to the 100 du. And so then I take an antiderivative. I have u to the 101 over 101 plus c. And that's x plus 7 to the 101 over 101 plus c. So U substitutions let you simplify the way a function looks. And you can kind of ignore adding stuff. You can imagine if I had a 3 in front of the x, that means I have to divide by 3. So I have a 3 down here and a 3 down here. That's exactly what happened with ax plus b earlier. But okay, let's do a few more examples. Here I'll just kick it off. So u would be the 3 minus 10x cubed. And then du, we get negative 30x squared dx. And so now I have to solve for what I have up in my integrand. And let's see, so I have to divide the negative 30 over, so I have 1 over negative 30. And then I have the integral, and it looks like it's going to be u to the 4th du. And then from here we can solve. Okay. This guy, it also uses the same technique from down here. It's a function that I know, e to the x, but instead of, or here I just should have said e to the t, but instead of just t, I have 3 times t. So we should expect our final answer is a 1/3 e to the 3t, because just like over here, we have a 1 over a, and then the thing we know. All right, so if I let u equal 3t, du is equal to 3 dt. So I have to bring that 3 on over. I have 1/3 du is equal to dt. And sure enough, we get 1/3 antiderivative, oops, e to the u du, and I'll let you solve it from there. All right, last one. You know, maybe you get confused on what you should let your u be. And if you choose the wrong u, and my computer might die, but hopefully I can put this in, maybe you think u is going to be cosine x squared. And you try stuff. When you do your substitutions, it won't all cancel, and it won't all be in terms of u. Notice everything up here, I get just things in terms of u, things in terms of u, things in terms of u. And that's a sign that I did the correct substitution. Okay, so I don't want the cosine. I actually want the sine, x squared. And then du is 2x cosine x squared dx. So let's divide that 2 over. 1/2 du is equal to x cosine x squared dx. So I have 1/2 integral, and all of this kills all of this, and so I just have 1 over root u du, and I'll let you solve it from here. All right, so there's a bunch of examples on how to do u sub, and at the end of the day, all it is doing is unpacking the chain rule. Okay, see you next time.